Good morning, student. Today we are going to learn about basic NMOS inverter. After the completion of today's session, you are able to discuss the operation of an ideal inverter and explain the operation and VTC curve of a basic NMOS inverter. So, ideal inverter. In this inverter, both input and output are represented by node voltages. So, in ideal inverter circuit, both the input variable A and the output variable B are represented by node voltages. Here, the Boolean value of 1 means logic 1 can be represented by a high voltage, that is VDD, and the Boolean value of 0 means logic 0 can be represented by a low voltage of 0. So this one is the truth table of an inverter, that when we give input 0, then we get a high output. When we give a high input, we get a low output. So let's see. This one is the VTC curve. VTC curve, which is a plot of input versus output voltage. The VTC indicates that for low input voltage, the circuit output is high. For high input voltage, the output decreases towards 0 volt. And this one is a ideal VTC curve of a ideal inverter. So the voltage VTH is called the inverter threshold voltage. We know that threshold voltage is required to turn on a MOSFET. So the output switches from VDD to 0 when the input is equal to VTH. So this point is the VTH point. So when the input voltage is between 0 means 0 to VTH, the output voltage is equal to VDD, and when the input voltage is between VTH to VDD, the output voltage is equal to 0. Here we can see. Thus, an input voltage, when it is in between 0 to VTH, then we can interpret this, or this is interpreted by this ideal inverter as a logic 0. Means when we give 0 voltage up to this point, logic 0, at that time we get at the output a logic 1. But when in this region we give a logic 1 value, and at the output we get a logic 0 output. So it satisfies the function of a inverter. So this is all about ideal inverter. Next is the basic NMOS inverter. The input voltage of the inverter circuit is the gate to source voltage of the NMOS transistor. Vin equal to VGS, while the output voltage of the circuit is equal to the drain to source voltage, that is Vout equal to VDS. The source and the substrate terminals of the NMOS transistor are connected to ground potential. So VSB equal to 0. And the NMOS is used here as a driver transistor, And why NMOS used as a driver transistor has been already discussed in the video of CMOS transistor. Next is the load device, means the upper part. So the upper part of the inverter acts as a load. So this one is the circuit diagram of the inverter. Here is the input, which is equal to the gate to source voltage, and here is the output, that is drain to source voltage. And here we can see the source and the body terminal of the NMOS is grounded. So VSB equal to 0, and this one act as a driver circuit, and this upper part is act as a load circuit or load device. So the drain of the NMOS, which terminal? This one. The drain of the NMOS is connected to the output terminal. Then the load device is represented as a two-terminal circuit element with terminal current IL and terminal voltage VL. Okay. Then one terminal of the load device is connected to the drain of the NMOS, means this terminal is connected to the drain of the NMOS, while the other terminal is connected to VDD, that is power supply, this terminal. This is a lumped capacitance Cout, which is used to represent the another MOS inverter connected to the output terminal. Okay. Next is the VTC curve, voltage transfer characteristic. So applying Kirchhoff's current law to the circuit, basic NMOS inverter circuit, we see that the load current is always equal to the NMOS drain current, that is IT equal to IL. So the voltage drop across this load is negligible. Because of that, the IL is equal to IT. Okay. So for very low input voltage levels, the output voltage Vout is equal to the high value of VOH. So in ideal inverter, we see that for low value of input voltage, we get a output, that is VDD. But that one is a ideal characteristic, ideal VTC characteristic. But here is a practical circuit. So we never get a exact value of VDD. It is nearly equal to VDD. So it is here denoted as VOH. Okay. So here we can see that this one is the maximum output voltage. So in this case, the driver NMOS transistor is in cutoff and hence does not conduct any current. As we know, this is a enhancement type NMOS transistor used in this circuit, and to turn on a enhancement type NMOS transistor, we need a positive voltage that we denoted as threshold voltage. So below threshold voltage, it is always in a off condition and there is no current flows through it. Next, the voltage drop across the load device is very small in magnitude, so the output voltage is high. As the input voltage Pin increases, the driver transistor starts to conducting a drain current and the output voltage starts to decrease. So when threshold voltage reaches, at that time the NMOS turns on and slowly the current starts to flow, and here also gradually the output voltage starts to decrease.